So equally likely outcomes just means that everybody has the same chance of occurring, okay? With classical method, you do not have to perform the actual trials, okay? You just know the odds. So remember how I asked you to flip a coin, what was the probability of getting heads, and you guys told me 50%? Did we actually flip a coin? No. We just know the odds, all right? What about rolling a die? We know we have a 1 out of 6 chance. What about drawing a certain card out of a deck of cards? We know there's 52 cards, 13 of each suit, so forth. All those are classical methods. It's when you don't have to perform the actual thing, you just know the odds, all right? So I have an example here. Throwing a fair die because each number has a same chance of occurring, a 1 out of 6 chance, all right? So help me out here. How are we going to figure out these odds? Guess what? It's basically the exact same formula of the empirical method. How many times did we perform this event? That's your denominator. How many times did your event occur? That's your numerator, okay? So let's look at what they say. They say if an experiment has n likely outcomes, and if the number of ways that an event E can occur is m, then the probability of event E is denoted with P of E. First of all, what does little n always stand for? Sample size. You got it. So just basically, how many times did you perform the event? That's going to be in your denominator, all right? So they try to make it look really, really wordy, but I think this is the best one versus these. I don't like these as much. Just how many possible outcomes could have happened? That's your denominator. How many times did event E that you cared about happen? That's your numerator, okay? I'm going to make this way more complicated than it needs to be, but I want to show why these work, okay? We're going to roll a fair die, compute the probability of rolling a number less than 5. Well, how many things can happen when we roll a die? What can we get in our sample space? 1 through 6. I more or less do it this way just so we still get comfortable with the vocab. What is a sample space? The sample space is what can happen when you perform your experiment. So if we're rolling a fair die, getting 1 through 6 is in our sample space. All right, event E is what we care about. In this case, it's a number less than 5. What numbers are less than 5? 1 through 4. So basically, there's 6 things that could happen, but of those 6 things, how many do we care about happening? 4. So the probability of event E is there's 6 things that could happen, but there's 4 numbers that we care about happening, which reduces to 2 over 3. If it's classical method, it's very likely that they'll have you keep it as a fraction because it's just kind of clean numbers, nice and easy like that. But if not, we could change this into a decimal. So let's do or 0.667. Or they might have you change it into the percent. So this would be 66.7%. And they'll tell you what to round to. All right. Do you need to do this every time? Absolutely not. I'm just doing this to show you it works with what they were talking about. The number of things in your sample space is the denominator. The number of things in your event is your numerator, and so forth. I just think, okay, what can happen? All right, there's 6 things that can happen. How many of those 6 things do I care about happening? 4 of them. There's a 4 out of 6 chance of happening. All right? Okay, guys, I know we're only a half hour in and we already look like we're ready to fall asleep. I don't think this hot room helps us. The next thing, I would probably never do this, but I just kind of want to show you how it works, how it's another method of figuring out probability. We're going on, say we're going on a 3-day trip, and where we're going is either sunny or rainy. So let's call it Florida, okay? Compute the probability of having exactly 2 sunny days and 1 rainy day. It doesn't matter what order. So we're going to be away for 3 days. What's the probability that we get 2 sunny days and a rainy day? So what we're going to do is we're going to do a tree diagram. So let's do the diagram kind of off to the side over here and leave a little bit of room to right here. Where we're going can be sunny or rainy. So kind of do it in the middle because we're going to branch off and make a tree. So say this is day 1. This is going to be day 2. This is going to be day 3. All right. So day 1, we get off the plane, we step out, it's sunny, we're putting on our sunglasses, okay, and we're going to go to Disneyland. Day 2, we wake up. What could happen on day 2? It could be sunny or it could be rainy. So day 2, it could be sunny or it could be rainy. And we're just going to start branching off all the different possibilities, okay? So let's say the first day it was sunny, the second day it was sunny. What could happen the third day? It could be sunny or it could be rainy. See what we're doing? We're trying to just come up with all the different little combinations. So the first day could be sunny, the second day could be sunny, and the third day could be sunny. Or the first day's sunny, the second day's sunny, and the last day's rainy. What could also happen was maybe the first day was sunny, but the second day was rainy. Doesn't he have 2 things that could happen on day 3? Yep, and you guys are going to see the pattern. Guys, those are all the possible ways that we could get off the plane and it's sunny that first day, and then things could happen on day 2 or day 3. All right? We're going to do the same branching system right below it, but going off of that first rainy day, okay? What could happen after that first rainy day? The second day could be sunny or rainy. And the third days could be sunny or rainy. All right? So what is our sample space? Our sample space will be made up of a combination of 3, some S's and some R's, okay? So let's see if we can figure out what all could happen. I just kind of start at the top and go down, okay? What could happen if you like sun? It's the best scenario for you. 1, 2, 3, all days could be sunny. All right? So we ruled out SSS, so he's done. But what could also happen? You could start with 2 sunny days, but what could happen on the third day? It would rain. So what would we have? SSR. Guys, these are the only 2 scenarios where the first day and second day are sunny. We have sun, 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 or sun, sun, rain. We're kind of done with this branch now. All right? And we're going to go do the same thing down here. Sun, rain, sun. Or what could happen? Sun, rain, rain. So, those are the only 4 scenarios where the first day is sunny. We're going to just go down to the bottom half and do the same thing where the first day is rainy, okay? It's still all in our sample space. What could happen? Rain, sun, sun. Or rain, sun, rain. So that's that first half of that branch, right? Rain, sun, sun, or rain, sun, rain. All right, the bottom half, guys, we have rain, rain, sun. Or the worst to me would be rain, rain, rain. Phew, we did it all, okay? What's the point of this? Because now that we have our sample space, we can see how many different things could occur. So we have our denominator. And then we just have to go back and figure out what our event E is and see how many things we care about occurring. So let's figure out event E. What do we care about? 2 sunny days and 1 rainy day, okay? So does this count? Nope. Does that count? Yep. So we'll have sun, sun, rain. Does this count? Yep. Because it doesn't matter the order, right? We're just looking for 2 S's. Does that count? No. This guy. Okay, that's it, right? So when they ask us what's the probability, our probability of event E would be how many total things could happen. There was 8 different combinations of weather, but how many did we care about happening? 3 of them. Okay? So our answer is 3/8, or what's that end up being? 0.375, I think. Or 37.5%. Guys, this is pretty tedious, but I wanted to do it in your notes because I want you to realize this tree diagram that we just drew could be the exact same tree diagram that you use for any experiment that has only 2 outcomes, but you're doing it multiple times. For example, having a kid. You can have a boy or girl. So I could ask you, what's the odds that you have 3 kids and you get 2 girls and 1 boy? This could be the exact same thing, right? replace S for G, with G for girl, replace rainy days for boys. If I have kid 1, kid 2, kid 3, and there's 2 genders, each can go, here's my sample space, here's my outcomes. I have a 3 out of 8 chance of getting 2 girls and 1 boy if I'm doing it. Tossing a coin, heads or tails. If I toss it 3 times, here's my sample space of getting 2 heads and 1 tail, all right? So this tree diagram can be used for any event that has 2 outcomes that's performed 3 times. All right, the next thing is, how many of us actually want to do this, though? Because the whole idea is the more you can do something, the better and the more accurate results are. But who wants to sit here and flip your coin 100 times? We don't. So what we want to do is we use simulation. Simulation's either using a calculator or a computer. If you guys could get out your calculator. Now those that have the newer ones, yours are a little bit better. I got to remember where we got to go, though. The program apps. Okay. So on your calculator, kind of dark, if you hit this apps button right here, there's a bunch of different apps. Can you guys see that? There's a bunch of different apps. If we want to scroll down to probability simulator, so go find probability simulator. So scroll down until you see probability simulator and go ahead and click it. You guys are young. Like, I have to keep in mind that I've been teaching over 12 years and that I'm getting older, but you guys are all staying the same age. But did anybody play the old school, like, Nintendo Game Boys? Yeah. This, like, reminds me of it, where it's just that green and black screen. There's no color or anything, you know. So this probability simulator is way cooler. Like, I should have Abby's probably, because she gets to do hers in color, so it's really neat. So the whole idea here is, if we have time, and I doubt we do this, I think you guys are at a point where, like, you don't necessarily need to do the simulation to understand what we're doing, but it can do a variety of things. It can toss coins, roll dice, pick marbles, spin a spinner, and draw cards, okay? So say we really do want to toss coins, but I don't have enough quarters for everyone. We could go and toss coins. And if you look, it's going to keep track of my tails and my heads, and I just have to hit the window button to toss my coin. And look, it tossed it, and the heads landed, okay? And maybe you're like, okay, well, pushing that 1,000 times is still like flipping a coin 1,000 times. So it lets you kind of do it quicker. So say I want to toss it 50 times. I can hit trace, and it will just do it real quick, and I'll show you, see it go up, down. This is it tossing 50 times. And it can give you an idea of how many tails and how many heads you get, which is kind of cool. So it's just keeping track, okay? So you can go and arrow to it, and it tells you your frequency. So of the 50 coin tosses, 24 were tails, and 26, oh, I did 51 because I did the first coin flip. 27 were heads. So it's kind of neat. All right, so then escape out of that. Escape again. Are you sure you want to leave? Yes, this is the hardest part. Like, they don't want you to leave. I think drawing cards is the next coolest thing, and I might steal Abby's because hers is legit red and black, okay? So if you draw cards and you hit window, draw, it will flip the coin and keep track of what cards you can draw, okay? So I might do an experiment where I'll say, hey, everybody draw 5 cards. What's the probability that you get 2 hearts or something like that? And so we can calculate our probabilities based off of that. You can draw another card, and it'll flip it, and I'll just keep track for you, okay? So it's kind of cool to see, now that you guys know where the stuff is, but it's kind of cool to just see what your calculator can do. It's pretty impressive. Abby, are you on the card one right now? Mm-hmm. Can I steal yours? So anybody else that has the newer one, look how cool that is. I know, right? So you draw it, and it flips, and she gets actually in black and red. Kind of neat. I know. I like this too. You probably haven't. You had to use it for algebra at all? Okay.
Actually, my sister's got
Okay. So I like these too, because if you guys ever had to use them for graphing in algebra class, and you had to graph multiple lines, each line's a different color. Which, like, you know you're a math teacher when you get excited about that stuff, right? You know you're a math teacher when, okay? So that's just something to kind of keep in mind. We'll be talking about all these different things, but how it's actually done a lot of times is done by using some kind of computer program that we won't actually do ourselves. All right? So let's look at this last one here. Subjective probability, it's our third probability. What's it mean to be subjective? It means you have a little bit of opinion or bias with it. Like a lot of people say math is objective, it's black and white, you know, you're either right or you're wrong. Where an English class might be subjective because based on your teacher, they might prefer a certain style of writing over others. So how does that roll into our probability? Subjective probability is a probability obtained, but it has a little bit of judgment going on, okay? And you'll see this in sports, medicine, and weather. Where might you see it in sports? Well, you can look at records, but don't people always have a little bit of bias of favorite players or favorite teams or whatever it may be, or maybe favorite positions, right? So maybe the Cardinals, I haven't been following the Cardinals. The Cardinals aren't doing right. Where are we? Okay, so we're done. But you know, like how you have an idea of what your team's like, and so you know the odds of them going somewhere, but then someone might like the Cardinals because their pitchers hit better than other pitchers or something like that, right? There's always a little bit of judgment there, and so that's why it's subjective probability. Medicine, not to scare you, but you know, surgeons or whoever have certain odds of performing surgeries, right? And so they could do empirical probability with, I've done this 100 times and 99 times it's been successful. But there's always a little bit of bias because each person in each scenario is a little bit different. Weather. Have you guys heard the joke about where I want a job where I can be wrong and still get paid? The weatherman, right? That's the whole idea there. These weathermen aren't just going outside and looking outside and say, oh, it looks like it's going to rain today. They have actual radar and they're calculating certain probabilities, but they're always going to have a little bit of bias because they're using their own knowledge to follow things there. All right? Subjective probability, guys, you can never calculate it. You need to be able to recognize it, okay? So like it might be like more of a definition than an actual probability, okay?